Welcome back to the deep dive. I recently came across a concept that truly bent my mind, and I think it will yours too. Imagine a computer that sips power like a nightlight, fits in the palm of your hand, and can learn and adapt in real time, just like, well, us. For me, the idea that its ultimate blueprint has been right there, evolving for billions of years. The human brain is even more captivating. It's a masterpiece of low-power, parallel computation packed with over 100 billion neurons and 100 trillion synapses. Just incredible numbers. Okay, let's unpack this. Our mission today is to deep dive into the incredible quest to mimic this biological marvel with something called neuromorphic engineering. And we'll explore the cutting-edge, large-scale spiking array processors that are making this ambitious dream, well, a reality.
What's truly fascinating here is just how profound the brain's efficiency is, especially when you consider, well, think about this. A personal computer uses an astonishing 40,000 times more power, and it still runs 9,000 times slower than even a mouse brain for certain kinds of cortical simulations. A mouse brain.
40,000 times the power. That's hard to even grasp.
It really is. And if we connect this to the bigger picture, simulating a human-scale brain, which is a goal of some major scientific projects, could require an exascale supercomputer. And that supercomputer would consume as much power as maybe 250,000 households.
Wow.
So this raises a really important question. How do we possibly bridge that colossal gap between biological computation and, our artificial attempts? It's not just about raw speed. It's about a fundamental shift in architecture and energy use, something biology perfected eons ago.
And that's exactly what we're going to explore today. This deep dive is inspired by a really comprehensive review article titled Large-Scale Neuromorphic Spiking Array Processors, A Quest to Mimic the Brain. This article, published in Frontiers in Neuroscience, brings together researchers from, well, all around the globe, all at the forefront of this diverse and rapidly evolving field. Our goal for you, our curious listener, is to understand the fundamental principles behind neuromorphic engineering, and also the key challenges these brilliant minds are tackling, and the most significant advancements they're making in building these brain-inspired computing systems. We'll be looking at several prominent neuromorphic chips, comparing their designs, their capabilities, and the exciting real-world applications they promise. Get ready to have your mind expanded. So we've talked about the why, that incredible efficiency of the brain, but for our listeners who are maybe already clued into the world of AI, let's go a step deeper than just what is it? What's the fundamental departure and philosophy behind neuromorphic engineering? What truly sets it apart from, say, traditional computing?
That's a great way to frame it. At its core, neuromorphic engineering, or NE, is an interdisciplinary field. It draws direct inspiration from neurobiological systems for, information processing. But here's the crucial distinguishing feature. It's fundamentally different from conventional computing, what we usually call the von Neumann architecture.
Ah, the von Neumann architecture. Separate memory, separate processing.
Exactly. And with NE, we're not just talking about making faster chips. We're talking about designing chips that compute in a brain-like way, meaning they are inherently adapted to perceive, learn, and adapt. It's a different computational paradigm.
It's almost like traditional computers are trying to run a marathon in hiking boots, maybe. While the brain is this perfectly streamlined runner, this paradigm shift isn't just about faster silicon, it's about fundamentally rethinking how information flows and is processed, isn't it? What's the biggest hurdle in making that fundamental architectural leap? It sounds challenging.
You've hit on a crucial point. The biggest hurdle is really overcoming decades of engineering principles built around that von Neumann architecture. It's deeply ingrained. That's why NE has these fascinating dual goals. On one hand, there's a scientific goal. Researchers aim to understand the computational properties of biological neural systems by, well, implementing models in integrated circuits, or ICs.
So, building chips to understand biology.
Precisely. Think of it as building a working physical model of a brain circuit to test theories about how our own brains work. It provides this powerful feedback loop to potentially unravel biological mysteries.
That makes sense. We're not just building brain-like systems, we're actually using them as tools to understand the brain itself. That's a powerful feedback loop indeed. What's the other side of that coin then?
The second is an engineering goal. This is more about exploiting the known properties of biological systems, their incredible efficiency, massive parallelism, and extremely low power consumption. It's about using those properties to design better, more efficient devices for real-world applications. It's about creating practical technologies that truly benefit from the brain's optimized design, rather than just brute-forcing complex AI tasks with ever larger, power-hungry traditional systems.
Okay, so why is the brain the ultimate inspiration for all of this? I mean, besides its obvious intelligence and, creative abilities, what makes it so special from an engineering perspective?
Well, the brain really represents the pinnacle of computational complexity, efficiency, and robustness, especially when you consider its incredibly low power and small size constraints. It's tiny. It's massively parallel and redundant. That means it can handle many tasks simultaneously and keep functioning even if some components fail, which is remarkable.
Resilience, yeah.
And critically, it excels at pattern recognition and association with incredible precision and efficiency, even when operating with inherently noisy and unreliable individual components, like neurons. This is something conventional computers struggle with immensely. They need perfect inputs, perfect components.
And this brings us back to that von Neumann bottleneck you mentioned earlier. It's like the brain has already solved this fundamental computer science problem, almost by accident.
Exactly. The brain fundamentally sidesteps the von Neumann bottleneck, that data traffic jam, where traditional computers constantly shuttle information between separate processing and memory units. Imagine having to drive to a library every single time you need to think about a new fact. It's inefficient.
Right, constantly fetching data.
The brain and neuromorphic systems try to emulate this, integrate that library directly into the thinking process. They co-localize memory and computation. This dramatically reduces power consumption and latency. It's a core principle.
That certainly paints an exciting picture for the future of AI. But with such a radical shift in architecture, are there any inherent trade-offs or new challenges these systems introduce compared to traditional computing? And more importantly, what are the concrete advantages of these neuromorphic emulators for us, the listeners, thinking about the next generation of tech?
That's a crucial, balanced question.
Yeah.
While there are challenges, particularly in programmability maybe, and interfacing with the existing digital infrastructure, the advantages are compelling. First, as we highlighted, high energy efficiency is paramount. We're talking orders of magnitude lower power consumption compared to traditional systems. Huge difference.
Orders of magnitude, that's key.
Second, they boast a massively parallel and distributed architecture mirroring the brain's own structure. This allows for simultaneous processing across countless units. Third, they require a small silicon area, enabling compact and portable devices, which is ideal for edge computing, think sensors, mobile devices.
Things you carry around, yeah.
And finally, they are particularly suitable for real-time, large-scale neural emulations. The processing speed can be largely independent of the network size, unlike traditional simulations. This real-time, always-on capability is critical for systems interacting with the real world, like autonomous vehicles or robotic perception. They need to react instantly.
That sounds like a game changer for so many applications. What's the market outlook for these chips? Is this just academic theory, or is it becoming a tangible industry, something we might see in products sooner rather than later?
Oh, far from just theory. This field is generating significant excitement and investment. Neuromorphic engineering was listed among the top 10 tech breakthroughs back in 2014 by MIT Technology Review, and among the top 10 emerging technologies of 2015 by the World Economic Forum.
So it's been recognized for a while.
Exactly. The neuromorphic chip market is expected to grow exponentially. It's driven by the increasing demand for advanced AI and machine learning systems that traditional architectures just struggle to power efficiently. It also offers a compelling solution as Moore's law. The exponential growth in transistor count approaches its physical and economic limits. We need new paths. This isn't just a new type of chip. It's potentially a new, sustainable path for computing.
So it's not just a potential future, but something that's already in commercial products. Give us some examples to show how this is already making an impact. Make it real for us.
Absolutely. Several neuromorphic systems, or systems inspired by them, are already in commercial use, demonstrating practical viability. For instance, Synaptics Inc. They develop touchpad and biometric technologies for portable devices, leveraging neuromorphic principles for efficient pattern recognition.
Okay, I've heard of Synaptics.
Yeah. Foveon Inc. uses CMOS color imagers that mimic aspects of biological vision. CryonoCam Inc., which is now Prophecy, builds asynchronous time-based image sensors. These sensors respond only to changes in the visual scene, just like our own eyes do at a very fundamental level, much more efficient than sending full frames constantly.
Event-based vision. That makes sense.
Even the old Logitech marble trackball utilized an artificial retina for cursor movement decades ago. And Inalab's LTD's dynamic vision sensor, or DVS, is another successful example. It captures visual information with unprecedented efficiency, only detecting events when pixels change, not constantly scanning. These are all early examples showing the practical viability and commercial potential of neuromorphic design thinking.
Here's where it gets really interesting for me. The brain doesn't compute like a traditional computer with separate processing and memory units. It's all intertwined. This deep dive shows how these chips are moving beyond simply faster to smarter by fundamentally rethinking architecture. It's not just about speed, it's about a different kind of intelligence. The implications of co-localizing memory and processing, essentially bringing the library right into the thought process, seem enormous.
Well, this raises an important question, doesn't it? Can we achieve true adaptive intelligence without mimicking the brain's fundamental operating principles? The move away from the von Neumann architecture, where memory and processing are separate, is a potential game changer for efficiency and scalability. It's about designing systems that are inherently adapted for the kind of tasks the brain excels at: perception, learning, adaptation, rather than forcing brain-like tasks onto architectures designed for, sequential deterministic math problems. It's a much more holistic approach that could perhaps unlock levels of AI we've only dreamed of.
All right, now that we've set the stage and understood the why, let's get into the nitty-gritty. We're going to dive into some of the most prominent large-scale neuromorphic processors mentioned in our source material, each with its own ingenious approach to mimicking the brain. We'll explore their unique contributions and what makes them stand out. Let's start the tour. Hashtag 2.1. Integrate and Fire Array Transceiver, IFAT, and its variants. Let's kick off our tour with the Integrate and Fire Array Transceiver, or IFAT. This system seems pioneering in its approach to event-driven communication, which you said is fundamental to how the brain operates. What's the core idea here?
Right, the IFAT is a mixed-mode VLSI-based neural array. VLSI is very large-scale integration, basically how we pack transistors onto chips. It's designed with reconfigurable weighted synapses, but its defining characteristic is its use of the Address Event Representation Protocol, or AER.
Address event representation. Break that down.
Okay. When a neuron fires in this system, it doesn't send a continuous signal. It simply outputs its unique address. That's the Address Event Representation. It's a digital event signifying its spike. Think of it like neurons sending little digital postcards with their return address, not shouting constantly, makes communication incredibly efficient.
Got it. Just the address, just the event.
Exactly. And the network's connectivity is then handled by a lookup table, or LUT. This LUT stores information about where these addresses should be routed, and also the strength and polarity, meaning excitatory, like hitting the gas, or inhibitory, like hitting the brakes of the resulting synaptic connection.
So it's all about event-driven communication, very brain-like. And these connections, they aren't just simple on-off switches, right? They're more nuanced than that.
That's correct. Early IFAT designs used probabilistic synapses, where weights were represented by a probability, adding a touch of maybe biological randomness or uncertainty. Later versions evolved to use conductance-based switch capacitor circuits. Here, the weight became proportional to the amount of charge integrated onto the destination neuron's membrane capacitance. This offered much more precise and tunable control over the synaptic strength.
And there are a couple of fascinating variants of the IFAT mentioned. The MFAT and higher IFAT, these seem to really push its capabilities. Let's start with MFAT. What's the innovation there?
Right, the MFAT, which stands for Mihalis-Niebuhr and IFAT, was developed with three main design goals in mind: maximize neuron array density, minimize power consumption, and reduce mismatch between neurons due to manufacturing variations. What's truly insightful here is that MFAT's Mihalis-Niebuhr MN neurons aren't just simple integrate and fire neurons. They're capable of producing 9 distinct, prominent biological spiking behaviors.
9, like
Things like regular spiking, bursting, firing in rapid succession, or adapting their firing patterns over time using an adaptive threshold. This isn't just an incremental improvement. It's a huge leap toward modeling the subtle, complex rhythms of the brain, rhythms that are critical for higher-level processing. And it does this while sipping power. It suggests that fidelity to biological dynamics might actually be key to unlocking certain computational efficiencies.
That's a huge leap in biological fidelity. How do they achieve that and efficiency, considering how complex those 9 behaviors must be to model?
They do it through clever circuit sharing. A single membrane synapse, a single comparator which acts as the neuron's soma or body, and a single threshold adaptation element. These are ingeniously shared across all the neurons in the array.
Ah, sharing resources.
Exactly. This design leads to significantly less power consumption, around 360 picojoules per synaptic event, which is tiny. An impressive density, too, packing nearly 670 integrate and fire neurons into just a square millimeter of silicon. It's a prime example of how clever design, inspired by biology, leads to practical miniaturization and extreme energy savings. It also achieves more controlled mismatch between neurons, which can be beneficial depending on the application, believe it or not. Sometimes a little randomness helps.
And what are the MFAT's practical applications? Where could we see this kind of brain-like processing make a difference?
Well, beyond precisely mimicking biological systems, due to its reconfigurability and diverse spiking behaviors, which is great for neuroscience research, the MFAT is incredibly well suited for low-power visual processing tasks. This includes real-time linear filtering, edge, and smoothing operators for image enhancement, and even image dewarping, where incoming events can be dynamically projected to new locations in the neural array based on, say, camera movement.
So real-time vision processing on the edge.
Exactly. It's ideal for low-power visual preprocessing in advanced technologies like autonomous cars and drones, for tasks such as efficient object recognition and classification right at the source, without needing to send massive data streams to the cloud for processing. Saves bandwidth, saves power.
Now let's look at the higher IFAT. That name implies something about hierarchy, which sounds like it's tackling the issue of scale, maybe.
Indeed. The higher IFAT, or Hierarchical Address Event Routing IFAT, addresses a major challenge for scaling neuromorphic computing up towards human brain complexity, specifically accommodating massive, flexible, long-range synaptic connectivity. How do you connect billions of neurons efficiently over longer distances?
The brain's white matter problem, but in silicon.
Precisely. Higher IFAT proposes a multi-scale system architecture, much like the gray and white matter organization in the brain itself. It combines efficient, dense local connectivity, think gray matter, with flexible, sparse, long-range connectivity like white matter tracks. This hierarchical structure is crucial for truly large-scale networks.
So how does it achieve that long-range communication efficiently?
The higher protocol itself provides scalable, long-range neural event communication specifically optimized for these locally dense and globally sparse connections. It's tailored for that structure. On a single chip, it can integrate up to 65,000 neurons and achieves remarkably low power consumption, down to an astounding 22 picojoules per spike. What's truly impressive is how it enables such complex communication without blowing out the power budget. It's all about efficient routing.
22 picojoules per spike. And looking ahead, what's the future for higher IFAT? How could this technology evolve even further?
While future optimization involves integrating nanoscale memristor synapse arrays, these could potentially replace the external DRAM memory lookups, which are currently used to store synaptic connection information.
Memristors, those emerging memory types.
Yes. Integrating them could lead to even greater density and energy efficiency, potentially achieving sub-picojoule per spike levels, a truly incredible feat of power reduction. Applications are vast. Things like online unsupervised learning with event-driven contrastive divergence, generative models of probabilistic spike-based neural representations. Also, big vision inference in deep networks and large-scale simulation of cortical models for computational neuroscience. It's also accelerating spike-based learning methods for adaptive intelligence, meaning systems that can learn on their own in real time.
So we've seen how dedicated chips like IFAT are pushing the boundaries of event-driven, low-power processing. But what if you don't want to build custom hardware every time? What if you want to model something on the scale of a cortex without needing a multi-million-dollar fabrication plant? That's where products like Deep South come in, it seems, leveraging more accessible hardware for truly massive simulations.
Deep South is indeed a cortex emulator, designed specifically for simulating very large and structurally connected spiking neural networks, with direct inspiration from neurobiology. It was developed in Australia, hence the name. What's distinct about Deep South is its modular structure, mimicking the hierarchical organization of the brain itself, particularly the neocortex.
How does it model the brain's modularity, those repeated structural patterns we see in the cortex?
Its basic building block is the mini-column. Each mini-column consists of 100 neurons and is considered a fundamental functional and anatomical unit of the cortex. These mini-columns can have up to 8 programmable neuron types, allowing for diverse local computations within that small unit. These mini-columns are then grouped into hypercolumns, which can contain up to 128 mini-columns, acting as a larger functional grouping. This hierarchical structure allows for efficient representation and scaling of brain-like networks.
That's a clever way to organize complexity, but simulating billions of neurons still sounds like a massive undertaking. Requires a lot of physical silicon, right? How does Deep South handle the sheer scale?
That's where its innovation in scalability and efficiency comes in. Deep South doesn't physically implement all neurons on dedicated silicon like some other systems. Instead, it leverages the high speed of FPGA's field-programmable gate arrays, which are reconfigurable hardware chips through time multiplexing,
Time multiplexing.
like sharing.
Exactly. It means a single physical mini-column on the FPGA can simulate 200,000 time-multiplexed virtual mini-columns in real time. It rapidly switches between simulating different virtual units. This clever approach allows it to simulate up to 2.6 billion leaky integrate and fire, or LIF, neurons in real time. And if you slow it down to 5 times slower than real time, it can scale to an astonishing 12.8 billion LIF neurons. The limit becomes the FPGA's memory resources.
Billions of neurons. That's approaching human brain scale, numerically at least. But how does it handle communication between all these virtual neurons without getting bogged down in a data traffic jam, especially when it's all-time multiplexed? It uses a sophisticated hierarchical communication scheme. Crucially, it models the structural, rather than purely random, connectivity of the neocortex. Instead of storing prohibitively large lookup tables for every single point-to-point connection, it stores connection types hierarchically.
Right.
This dramatically reduces memory requirements from potentially terabytes down to mere kilobytes.
Storing connection rules instead of individual connections. Smart.
Yes. And critically, communication between mini-columns uses event counts or spike counts over a time window, not individual spikes. This significantly reduces the communication bottleneck. This system allows one mini-column to efficiently propagate events to up to 200,000 downstream neurons with configurable axonal delays, mimicking how information might spread and integrate in biological circuits.
So it's essentially a software-defined, highly scalable architecture running on commercial, off-the-shelf hardware. Is it accessible for researchers who might not have access to custom, specialized chips?
Yes, that's a key advantage and part of its appeal. Deep South is implemented on commercial off-the-shelf FPGAs, like the Thoracic DE5 kit. This makes it much more accessible than many specialized neuromorphic hardware platforms that require custom fabrication. It also comes with a PyNN-like application programming interface, or API, in Python. PyNN is a common standard for neural simulations. This API enables rapid modeling of different neural network topologies and configurations, including precise spike monitoring. It fosters wider research community engagement, really democratizing large-scale neural simulation.
And what are its main applications? Who is using Deep South and for what kind of research?
It's primarily used by computational neuroscientists to run large-scale spiking neural networks. It helps them test theories of brain function at unprecedented scales, exploring dynamics that only emerge in very large networks. One specific application highlighted in the source material is the real-time emulation of the auditory cortex, allowing researchers to study how complex sound information might be processed in a brain-like manner.
Next up, let's talk about Brainscale S. The name itself suggests something grand and powerful, almost like it's trying to build a brain, not just simulate it. What's its core concept, and how does it differ from what we've seen so far? It sounds ambitious.
Brainscale S, developed at the University of Heidelberg in Germany, takes a truly unique approach. It's based on the direct emulation of model equations using continuous time analog circuits. So, the equations that describe neuron and synapse variables, the circuits directly implement them. What's revolutionary is that the electronic circuits act as physical models, implicitly solving complex differential equations. Electrical quantities like voltage or current directly represent model variables like membrane potential or synaptic current. It's almost like the silicon itself is the neural model, rather than just executing software instructions that represent the model.
That sounds incredibly efficient, almost like the circuits themselves are the brain models living and breathing in silicon. What specific biological model does it primarily use?
It primarily implements the adaptive exponential integrate and fire model, or ADX. This is a fairly sophisticated model that provides a rich set of neuron dynamics, including bursting and adaptation. But here's where Brainscale S truly stands out. It operates at an acceleration factor of 10,000 times faster than biological real-time.
10,000 times faster. Wait, so a process that takes, say, an hour in a real brain?
It takes less than half a second on brain scales, yes.
Wow. When I first grasped that, my initial thought was finally we can speedrun brain development. It truly feels like it changes the game for certain types of neuroscience research, doesn't it? But analog circuits, as you mentioned, can take up a lot of space. How do they scale this to large networks without the chips becoming impossibly huge, especially if they're running that fast?
They tackle that challenge through wafer-scale integration. This is really unique. Instead of dicing a silicon wafer into individual chips, which often means discarding the edges and losing valuable area, Brainscale S integrates an uncut silicon wafer containing 384 neuromorphic chips called high-can ASICs. They then use a special post-processing metallization scheme to interconnect these chips directly across the normal boundaries on the wafer itself. This effectively turns an entire wafer into one giant connected neuromorphic system. It's necessary to handle the immense communication bandwidth required by that extreme 10,000x acceleration factor.
So it's essentially a giant integrated circuit board made directly on the wafer. Incredible. Let's dig into the high-can ASIC a bit more. What makes these individual brain cell chips tick?
Right, the ECAN ASIC, that's the high input count analog neuronal network chip, is the heart of Brainscale S. It's the building block on the wafer. It features a symmetrical analog network core with synapse arrays enclosing neuron blocks. For communication within the core, it uses time multiplexing for event communication, similar to Deep South, allowing multiple neurons to share a channel efficiently. But for off-wafer communication, across the vast expanse of the wafer, it uses packet switching with digitized time information. True real-time analog communication isn't feasible over those longer distances due to signal degradation and latencies, especially at 10,000x speed.
So digital communication between the analog cores.
Exactly. A key feature for storing analog parameters, things like reversible potentials, threshold voltages, bias currents that define neuron behavior, is floating gate, FG technology. This allows for stable, precise, non-volatile tuning of the analog circuits. Its synaptic design uses a current mode implementation with 4-bit digital-to-analog converters for weights. It also includes circuitry for correlation measurement to implement spike timing-dependent plasticity, or STDP, which is a crucial biological learning mechanism.
What are the primary applications of such a unique, accelerated system? Who benefits most from being able to model brain processes at 10,000 times speed?
Its main strength lies in accelerating model processes. Think about exploring learning and development in neural networks, or searching through vast parameter spaces to find models that match biological data. These things would take weeks or months on conventional computers, but can be done much faster on Brainscale S. It's used for studying things like stochastic inference, pattern representation, and recognition with these accelerated analog neuromorphic systems. The ability to compress biological timescales makes it invaluable for certain types of neuroscience research, where you need to observe the long-term evolution of neural networks or test a huge number of parameter combinations very quickly.
Now let's explore Dynapse SL. The second L part sounds like it implies some kind of self-learning, maybe? Which is, a holy grail for AI. What's its fundamental approach, and how does it integrate learning right there on the chip itself?
Dynapse SEL is a sophisticated mixed-signal multi-core processor. It beautifully combines analog computation for neuron dynamics with digital asynchronous communication and routing for flexibility and scale. And yes, it places a strong emphasis on online learning, as its name suggests, meaning it can adapt and learn right on the hardware as it processes information, not just executing pre-programmed instructions. It's built using advanced 28-nanometer fully depleted silicon on insulator, or FDSOI processes. That's a fancy way of saying it's engineered at a microscopic level for extreme energy efficiency, which is key to its low power consumption.
So it's integrating both analog for the nuanced neuron dynamics and robust digital for communication and routing. How is its overall architecture structured to achieve this on-chip learning capability?
The chip comprises 4 non-plastic cores. Each of these has a 16 by 16 grid of analog neurons, and each neuron has 64 4-bit synapses. These are for general processing. But crucially, it also features one dedicated plastic core. This core has 64 analog neurons, but each is connected to 64 by 128 plastic synapses that have on-chip learning capabilities. It also has 64 by 64 programmable synapses. This dedicated plastic core is a significant differentiator, allowing for adaptive computations right on the hardware.
A dedicated learning core. Interesting. And for communication, what kind of routing does Dynapse SEL employ to connect all these cores and neurons, both plastic and non-plastic, efficiently?
It uses a highly hierarchical AER routing architecture with 3 distinct levels. Level 1 handles communication within a core. Level 2 handles communication between cores on the same chip. And Level 3 handles communication between different chips. It supports both source address routing, where the sender specifies itself, and destination address routing, where the sender specifies the target. It uses both SRAM and ternary content addressable memory, or TCM, memory structures for routing tables. TCMs are particularly fast for lookups. This hierarchical approach is highly scalable. It allows up to 16 by 16 chips to be connected in an array, achieving all-to-all connectivity without needing external support like FPGAs or computers, which is quite impressive for building large interconnected systems directly.
That's a lot of memory and processing units interacting. Does it run into that von Neumann bottleneck we discussed earlier, the data shuffling problem?
This system directly addresses that crucial bottleneck. The TCAM and SRAM circuits, which store routing information and potentially other data, are subdivided into small blocks. And these blocks are embedded directly within the neuron and synapse arrays.
Ah, co-localization again.
Exactly. This co-localization of memory and computation eliminates the von Neumann bottleneck, dramatically reducing power consumption and memory bandwidth requirements because data doesn't have to travel far. This design also opens doors for integrating emerging memory technologies like resistive random access memory, ReRAM, or memristors for even greater density and efficiency in future versions.
So it's inherently designed for learning, and it avoids the bottleneck. Tell us more about the plastic core and its on-chip learning abilities. That seems to be where the magic happens. Can you walk us through how it actually pulls off that on-chip learning?
The plastic core is indeed a highlight. It makes Dynap SL one of the only existing neuromorphic systems featuring on-chip online learning with analog neurons in such an advanced process node, 28mm FTSOI. It features 128 mixed-signal plastic synapses per neuron, each with 4-bit weight resolution, so 16 levels of strength. These weight updates are governed by 4-bit up-down counters that implement spike-driven learning rules. Rules inspired by biology, like the Brader model, or spike time-dependent plasticity, STDP-like mechanisms. The asynchronous memory control also allows for online reconfiguration of the routing tables themselves. This enables structural plasticity, meaning the connections can physically change over time, and potentially the implementation of evolutionary algorithms directly on the chip.
Yeah.
This is true hardware-based adaptation learning happening right in the silicon.
That's a huge step towards truly autonomous AI systems. What kind of practical applications can Dynapse SLL be used for leveraging this on-chip learning power?
Its capabilities make it suitable for a wide range of applications, particularly those needing real-time adaptation and low power. This includes biosignal processing, such as highly efficient auditory keyword recognition, spotting specific words in speech, and ECG anomaly detection, based on a technique called reservoir computing. In vision processing, it can be used for tasks like low-power face detection, object tracking, and obstacle avoidance in robotic systems. Its on-chip, real-time learning makes it particularly versatile for adaptive intelligence applications, where the system needs to learn and adjust in dynamic real-world environments without constant software updates or cloud connections.
The next one, 2DI FWTA, sounds like it's designed for a very specific, almost foundational type of neural network interaction. What's its core concept, and how does it mimic some of the fundamental dynamics we see in biological brains, like competition and cooperation?
You're right. The 2DI FWTA, or 2D Integrate and Fire Winner Take All chip, is specifically designed to implement cooperative competitive networks. These networks are characterized by populations of neurons with both recurrent excitatory connections, cooperation, and inhibitory connections, competition. These dynamics are fundamental to how brains process information and make decisions. The inhibitory connections mediate competition among neurons receiving different stimuli. Essentially, they fight it out, allowing the strongest signal or pattern to emerge. While the recurrent excitatory connections foster cooperation among neurons with similar response properties, helping to amplify and refine those strong signals. They reinforce each other.
And the winner-take-all part, what does that refer to specifically? Is it as simple as it sounds, one winner takes all?
Pretty much. In these networks, the group of neurons with the highest collective response effectively suppresses all other neurons, effectively winning the competition and becoming the dominant output representation. This allows the network to perform both linear operations, like analog gain and locus invariance, recognizing a pattern regardless of its exact position, and also complex nonlinear operations, such as nonlinear selection, making a clear choice, signal restoration, cleaning up noisy signals, and multi-stability, holding on to different states. These winner-take-all dynamics are believed to be widespread in the nervous system, from sensory processing to decision-making. So WTA is considered a fundamental computational primitive they've tried to capture efficiently in silicon.
This sounds like a powerful tool for understanding specific brain functions or for building systems that need to make clear choices from noisy inputs. How is this chip designed to achieve these dynamics efficiently?
The 2DI FWTA chip, implemented in a slightly older 0.35 micrometer CMOS technology, features a 2D array of 2048 integrated and fire neurons, arranged in a 32 by 64 grid. Each neuron receives inputs from AER synapses, as we've discussed. But crucially, the recurrent connections, those essential internal connections for cooperation and competition, are internally hardwired. They are not routed via the general AER bus.
Ah, so they bypass the main communication bus for those critical local interactions.
Exactly. This is a critical design choice. It prevents the AER bus from becoming overloaded and avoids prohibitive latencies when dealing with the dense, rapid recurrent connections required for these cooperative competitive dynamics. It ensures that the critical WTA dynamics happen quickly and efficiently in real time without communication bottlenecks. It supports local cooperation in 2D, connecting to the nearest neighbors, or 1D, connecting to neighbors along a line, allowing flexibility in network topology.
So it prioritizes those internal connections to keep things fast and efficient, even if it means sacrificing some programmability for those specific connections. What about its synapses? Are they special too?
It employs the DPI CNAP circuit, which stands for Differential Pair Integrator. It's known for its linear filtering properties. This linearity is important because it allows for multiplexing different spiking sources onto a single synapse. So a single physical synaptic circuit can effectively act as multiple virtual synapses. This helps optimize silicon area in a dense 2D array and maximize the number of connections possible.
What kind of research or applications has the 2DIF WTA been used for, given its somewhat specialized nature focusing on WTA dynamics?
Despite its specific motivation, the 2DIF-WTA functions as a general-purpose, large-scale pool of neurons for certain computational tasks requiring those dynamics. It has been used to evaluate models of global inhibition in insect olfactory processing, helping scientists understand how insects process smells so effectively. It's also implemented function approximation and inference using 1D cooperative competitive networks. And interestingly, researchers exploited the inherent device mismatch, slight variations in manufacturing, to create useful axonal delays for unsupervised learning of auditory features, mimicking how the brain might learn from tiny timing differences in sound.
Using the imperfections of the hardware creatively.
Exactly. Perhaps one of its most advanced applications demonstrated a real-time neuromorphic agent forming context-dependent visual tasks by configuring reliable finite-state machine computation on the chip. Finite-state machines are fundamental computing models. It's also been applied to auditory perception models in crickets and latency code processing in electric fish, showing its versatility in bio-inspired sensing and processing, especially where competitive dynamics are important.
Next, let's turn our attention to PARCA, which stands for Parallel Architecture with Resistive Crosspoint Array. This sounds like it involves a different kind of memory technology, maybe moving away from traditional transistors for the synapses, resistive arrays.
You're absolutely right. PARCA, developed at Arizona State University, fundamentally employs resistive random access memory, or RAM, cells arranged in a crossbar array structure. This allows for massively parallel weighted sums, essentially matrix vector multiplications, a core operation in neural networks, and highly efficient synapse weight updates. What's truly insightful here is how it replaces the sequential, row-by-row operations of conventional CMOS RAM-based approaches with simultaneous read and write operations across the entire RAM array. This is a radical shift from the von Neumann architecture, inherently integrating computation into the memory itself. The memory is the processor, in a way.
How does this RAM crossbar actually perform a weighted sum and do it in parallel? That sounds like the key operation.
Okay, in its read mode, to compute a weighted sum, like a neuron integrating inputs, a small read voltage is applied simultaneously to all the rows corresponding to non-zero input bits. This voltage is multiplied by the conductance at each crosspoint junction. You can think of the RAM cell's resistance, or rather its conductance, which is for resistance, as the synaptic weight. The resulting tiny currents flowing down each column are summed up naturally by Kirchhoff's current law at the column end.
Physics does the summing.
Precisely. This summed current then represents the total weighted sum for the neuron connected to that column. A column read circuit then converts this analog current into digital spikes or output values, mimicking the integrate and fire functionality of neurons. This allows for parallel reading and computation across the entire array in essentially a single step, significantly accelerating computation compared to sequential digital methods.
And how does it handle weight updates, learning? That seems crucial if the memory is the synapse.
In write mode, local programming voltages are generated at the row and column peripheries based on neuron activity. The column write circuit generates a programming pulse with a duration or duty cycle proportional to the column neuron's value, postsynaptic activity. Simultaneously, the row write circuit generates pulses proportional to the row neuron's value, presynaptic activity. The RAM cell's conductance changes based on the aggregate overlap time of these pulses applied across it. This effectively implements an Zaya learning rule, a mathematical operation crucial for algorithms like stochastic gradient descent, used in deep learning, or biologically plausible spike-based learning rules. So the learning itself is happening physically by changing the resistance of the memory cells based on neural activity.
That's a very hardware-centric way to implement learning. Has this been implemented in a real chip, or is it still more of a theoretical concept?
Yes, it's been demonstrated in silicon. They've built a test chip, a 64 by 64 neurosynaptic core, using RAM cells directly integrated within the CMOS process. This is called monolithic integration. This is crucial because it creates a compact and efficient unit where memory and computation are truly inseparable, addressing the von Neumann bottleneck at a fundamental material level. While this particular design used binary RAM, just on-off states, suitable for binary neural networks, the approach is being extended to multi-level RAM for more nuanced analog-like weights.
Now, RAM and other resistive devices sound incredibly promising for density and efficiency, but I imagine they come with their own set of challenges compared to mature CMOS technology. What are those, and how does Parka mitigate them?
That's a critical point, and a major area of research for all these emerging memory technologies. They're not perfect yet. Today's resistive synaptic devices have several non-ideal effects. These include limited precision in the synaptic weight levels compared to software's 64-bit floating point numbers. They can have nonlinear and asymmetric weight updates, meaning increasing the weight might behave differently than decreasing it. They have finite on-off ratios, significant device variation, both cell-to-cell and cycle-to-cycle, and voltage drop, IR drop, along the wires in large arrays, which can corrupt signals. A naive implementation using these imperfect devices can lead to poor accuracy. For example, the source mentions only 65% accuracy for MNIST digit recognition compared to an ideal 97% in software if you don't compensate.
Ouch, 65% isn't great. So how do they overcome these accuracy issues and make these imperfect physical devices behave reliably enough for complex AI tasks?
Researchers have developed several clever mitigation strategies at both the circuit and architecture levels. These are crucial for making our RAM practical. They include using a pacifier column circuit to eliminate off-state current leakage, which can mess up the sums. They use smart programming schemes or algorithms to improve the linearity and symmetry of way updates. They might use multiple RRAM cells to represent a single weight bit, averaging out some of the device variations. And they can relax wire widths in the array designed to reduce that IR drop problem. With these strategies applied, the source indicates that recognition accuracy can be restored to approximately 95% for MNIST. That demonstrates the practical viability of this approach despite the inherent device imperfections. It's a massive engineering achievement to bridge that gap.
That's much better. What are the target applications for Parka, where its parallel processing and integrated memory could make the biggest impact?
The system targets image and speech processing applications primarily. Demonstrations include efficient image and digit recognition and language modeling. Its ability to perform massively parallel matrix vector multiplication directly within the memory makes it highly efficient for these data-intensive tasks that are foundational to many modern AI applications, particularly those needing very low power and high throughput, like maybe edge AI or specialized accelerators, #TAG 2.7, transistor channel-based programmable and configurable neural systems.
Let's delve into a system that goes right back to the foundational physics, almost bypassing abstract models and directly using the properties of silicon itself. I'm talking about transistor channel-based neural systems. What's the core idea here, and how does it mimic biology so directly? It sounds really fundamental.
This approach, pioneered at the Georgia Institute of Technology, is fascinating. It models biological dynamics directly using the fundamental physical principles of MOSFET transistor channels. The key insight is truly profound. The physics governing ion flow in biological ion channels, which creates action potentials and other neural dynamics, shares striking similarities with electron and hole flow through MOSFET channels operating in certain regimes, specifically subthreshold. By exploiting these similarities, they can create incredibly dense circuits that effectively model biological soma behavior, the neuron cell body, with high fidelity, using the transistor's own physics.
So the transistors aren't just processing signals like neurons, they're physically acting like biological ion channels in some ways. That's a level of biomimicry I hadn't even considered before.
Exactly. This allows for remarkable efficiency and compactness. A spiking action potential circuit, for example, can be built using just 6 transistors and a few capacitors. That's astonishingly compact and efficient, very similar in component count to even the simplest abstract integrate and fire neuron models, but potentially capturing much richer dynamics. This allows for a very low-level, high-fidelity physical model that directly leverages the inherent physics of the semiconductor material itself.
And what about memory and learning in these systems? Can they integrate synaptic weights and adapt like biological systems do?
Yes, they utilize floating gate, or FG, devices for long-term analog memories and synapses. We saw floating gates in Brainscale S2, but here they're central to the learning aspect as well. These FG devices can store weights in a non-volatile manner, meaning they retain their value even when power is off, like flash memory. They could be programmed to generate biological excitatory postsynaptic potentials, EPSPs. And critically, they can also demonstrate biological learning rules directly. A single FG device can support hundreds of quantization levels, equivalent to maybe 710 bits of precision, even in scaled-down modern devices. This offers fine-grained control over synaptic strength.
That's impressive density for analog memory and precision. And it can actually perform biological learning rules like STDP.
Yes, these single FG devices enable long-term potentiation, LTP, strengthening connections, long-term depression, LTD, weakening connections, and spike time-dependent plasticity, STDP, where the precise timing of pre- and postsynaptic spikes dictates changes in strength. All of these fundamental learning mechanisms can be implemented through the physics of the same FG device. Cleverly, the learning circuitry itself is often placed at the edges of the synapse array, not within the synapse area itself. This helps maintain that incredibly high synaptic matrix density.
Has this approach been implemented in a complete neuromorphic IC, and what kind of complex behaviors has it demonstrated? Can it do more than just spike?
Indeed. An IC implementation has been built that integrates these biological model circuits for synapses, channel model somas, neuron bodies, and efficient input-output spike handling using AER. It uses a mesh architecture, or crossbar, similar to Parka but with different underlying devices, to achieve high synapse array density, connecting configurable channel neuron model components. This configurable array is essentially a specialized large-scale field-programmable analog array, FPAA. It allows researchers to wire up different neural circuits. As a proof of concept, it's been used to demonstrate optimal path planning in a maze, showing 100% correct and optimal performance across many scenarios. This shows its ability to solve complex goal-directed problems.
So it's not just basic neuron modeling, but can achieve complex behaviors like planning. What about something as intricate as dendritic computation? That's often simplified or ignored in many neural models due to its complexity, but it's thought to be important in real neurons.
This is where these systems make truly significant advances, pushing the boundaries of biomimicry. They've moved to include dendritic computation and FPAA reconfigurability. Dendrites are the complex branching import structures of neurons. And here's a mind-blowing insight from their research. They've shown that dendritic computation, using these analog circuits, is potentially thousands of times more energy efficient than typical analog signal processing for equivalent tasks.
Thousands of times more efficient. That's a huge claim. It suggests maybe we've been missing a trick by simplifying dendrites so much in our models. This could completely redefine low-power edge AI.
It absolutely could. It lends strong support to Carver Mead's original hypothesis. Mead is a pioneer of VLSI and neuromorphic engineering that physical or analog computation could be at least 1,000 times lower energy than digital computation for certain tasks. These transistor channel-based systems aim to realize this potential by building computation directly into the fundamental physics of the silicon. These reconfigurable ICs can create arbitrary dendritic structures with active and passive channel models, enabling complex tasks like word spotting from audio streams, roughly approximating hidden Markov model, HMM classifier structures, but potentially much more efficiently. The applications are vast: optimal path planning, building biologically inspired cortical structures, and developing highly energy-efficient embedded electronics for computation, classification, and learning systems. It truly offers a new wave of computing opportunities for energy-constrained applications, putting powerful AI capabilities into tiny, low-power devices. Hashtag Check 2.8. Other state-of-the-art neural emulators. Brief overview.
We've covered some really deep dives into specific architectures there, highlighting their unique contributions and philosophies. Now, let's briefly touch on just a few other notable large-scale neuromorphic systems mentioned in the source, just to round out our picture and see the breadth of innovation in this field. There are quite a few important players.
Certainly, these are equally important contributors, each with its own focus and strengths. First, NeuroGrid, developed at Stanford. This is a mixed-mode multi-chip system. It features 16 neurocore chips, totaling about 1 million neurons. It's designed primarily for large-scale neural simulations and visualization, using sub-threshold analog circuits that closely correlate to biological neuron characteristics. A whole board of 16 neurocores consumes very low power, roughly only 3 watts, showcasing its energy efficiency for simulation.
Okay, neurogrid for efficient simulation. What else?
Then there's True North from IBM. This is a major project. It's a purely digital neuromorphic chip. True North boasts 1 million digital neurons, spread across 4,096 cores per die. Each core holds 256 very simple neurons. Despite being digital, it achieves extremely low power consumption, just 72 milliwatts per die, or about 1 watt for a 16-chip board. This is primarily due to its fabrication in an advanced 28-nanometer technology and its strictly event-driven, asynchronous design. It supports various deterministic spiking behaviors and has been used for pattern recognition tasks, particularly in vision.
Very low power digital.
Next is Spinnaker from the University of Manchester in the UK. This is another digital neuromorphic array, but with a different philosophy. It's built on a multi-core system-on-chip architecture. Each node contains 18 standard ARM processor cores, the kind you find in phones. It prioritizes scalability and energy efficiency through brain-inspired communication methods, focusing on point-to-point message passing between cores using a custom interconnect. A single node can simulate around 16,000 digital neurons, depending on complexity, and massive systems with 500,000 cores have been built, making it a highly flexible platform for computational neuroscientists running diverse models.
So Spinnaker uses lots of standard cores with special communication.
Exactly. And finally, Loihi from Intel Labs. Intel's Loihi chip simulates about 130,000 neurons and 130 million synapses in real time. It's built on Intel's advanced 14-nanometer FinFET process. Loihi stands out for its on-chip training and inference capabilities. It supports various forms of synaptic plasticity, including different types of STDP, and incorporates programmable stochastic noise for probabilistic inference. Loihi has demonstrated significant energy delay product improvements, a measure of efficiency over traditional CPUs for certain optimization problems like lasso, highlighting its potential for complex learning-based computations beyond just simulation.
Wow, that's a truly diverse landscape of innovation. Neurogrid, True North, Spinnaker, Loihi, plus the ones we discussed in detail, like IFAT, Deep South, Brainscales, Dynapcell, 2DIFWTA, Parka, and the transistor channel approach. Each one seems to bring a unique strength to the table, solving different pieces of this enormous puzzle of how to build brain-like computers. So we've just toured a truly impressive array of brain-inspired computing systems, each with its own unique approach, its own philosophy. From the microscopic details of transistor channels mimicking ion flow in silicon, to wafer-scale systems running 10,000 times faster than biology, and massively parallel FPGA simulations. But what does this all mean for you, the listener, trying to grasp the big picture? Let's zoom out now and look at how these pioneers are tackling this immense challenge of mimicking the brain. How do they stack up?
If we connect this to the bigger picture, I think the diversity itself is a profound strength. There isn't one single right way emerging yet to mimic the brain, probably because the brain itself is incredibly complex and multifaceted. It does many things. The key really is to understand the trade-offs involved, the different design philosophies, and the specific problems each system is optimized to solve. They all contribute to a growing understanding of what's possible in both AI and neuroscience. It's a very rich field.
Let's try and break down some of those key differences then, starting with arguably the most fundamental one we've touched on, analog versus digital implementations. It seems like a core philosophical choice with big implications.
This is indeed a core distinction, yeah. Analog systems, like many of the IFAT variants, Brainscale is 2DIFWTA, the transistor channel systems, neurogrid, and parts of Dynapcell. They tend to be highly energy efficient and require less silicon area per neuron or synapse. They often operate in the sub-threshold region, where transistors behave more like biological ion channels, and small changes in voltage can have a big exponential impact on current. It's closer to biological physics in some ways. However, the downside is they can be more susceptible to process mismatch variations in manufacturing and inherent electronic noise. Though interestingly, sometimes this inherent stochasticity, this randomness, can actually be exploited computationally, as seen in the transistor channel systems for certain tasks like probabilistic inference.
So analog, efficient, compact, maybe noisy. And then on the other side, we had the digital approach, which is what most of our current computers use.
Correct. Digital systems such as IBM's True North, Spinnaker, the Deep South FPGA system, and Intel's Loihi are generally immune to those process variations and have inherent noise rejection. They offer predictable, deterministic, and robust computation. They also benefit more directly from technology scaling Moore's law, allowing more transistors, and thus more digital neurons, to be squeezed onto a chip as manufacturing improves. While they can consume more area and power per operation in general compared to pure analog, advancements in smaller feature sizes, like True North at 28 nanometers and Loihi at 14 nanometers, are rapidly mitigating this gap, especially when combined with event-driven techniques. A major advantage of digital is also the availability of precise software models for tuning parameters. It offers perhaps greater flexibility and easier programming compared to tuning analog circuits.
And many systems mix them.
Yes, many systems take a mixed signal approach, like Dynapt SL. They try to combine analog for the efficient spike computation and synapse integration with digital for robust communication and routing, aiming for the best of both worlds. And Deep South, as an FPGA-based system, leverages commercial hardware. It offers incredible flexibility for rapid prototyping and good scalability without needing custom chip design, making it very accessible for researchers.
So a lot of different flavors, each with its own pros and cons, but all striving for that brain-like efficiency in their own way. Let's talk about perhaps the most universally desired qualities, energy efficiency and density. How do these chips compare in how much power they sip and how many neurons they can pack into a small space?
These metrics are constantly improving and are really central to the whole field of neuromorphic engineering. That's often the main driver. Systems like the IFAT family, Parco with its RAM, and the transistor channel systems are specifically optimized for remarkably low power consumption, aiming for picojoule or even sub-picojoule energy per synaptic event. Dynapt being in that advanced 28 nanometer FDSRI process, achieves a very low energy consumption of just 2.8 picojoules per event and high neuron density, around 20 square micrometers per neuron. That's exceptionally efficient in terms of both power and space. Older analog systems like Brainscales, on 180 nanometer tech, are around 100 picojoules per event, while NeuroGrid, also 180 nanometer, achieves about 31.2 picojoules per event. More recent digital systems are catching up fast due to shrinking transistors. Loihi 14 nanometer comes in at around 23.6 picojoules per event, and True North 28 nanometer at 45 picojoules per event. Density also varies widely. We saw MFAT achieving around 669 neurons per square millimeter, while theoretical estimates for future 55 nanometer technology suggest over 55,000 neurons per square millimeter might be possible with further optimization. That's a staggering leap in miniaturization potential.
That's a significant range, reflecting the different design philosophies and, importantly, the manufacturing technology node they use. What about real-time performance and speed, especially for simulating complex, dynamic neural activity or interacting with the world?
For certain research, especially in computational neuroscience, speed or acceleration is crucial. Brainscale, as we discussed, is the standout here, operating at the astonishing 10,000 times biological real time. This is genuinely transformative for modeling learning and development processes that would otherwise take impossibly long timescales to simulate. Other systems, like higher error IFAT, are specifically designed for real-time operation at biological timescales, with average spike rates around 10 Hz, which is typical for many cortical neurons. This is important for interfacing with real-world sensors and actuators. Deep South, the FPGA system, is capable of simulating billions of neurons in real time, or even faster or slower depending on the configuration and available hardware. Most advanced systems ultimately aim for real-time or accelerated real-time simulation. This is essential for capturing and interacting with the complex temporal dynamics of neural networks, whether it's for scientific discovery or for practical AI applications that need to respond instantly.
Now, for something that truly defines intelligence and adaptability, maybe more than speed or efficiency, on-chip learning and synaptic plasticity, how many of these systems can actually learn and adapt directly on the hardware without needing to be constantly reprogrammed by an external computer?
This is a major area of active research and a key differentiator between systems. It's arguably where the field needs to make the most progress for truly autonomous AI. Some systems, like IBM's True North, NeuroGrid, the higher IFAT variant we discussed, and the Deep South FPGA system, are designed primarily with pre-computed weights. They currently do not offer general-purpose on-chip synaptic plasticity. Their learning, if any, happens offline in software, and the resulting weights are loaded onto the chip.
So they execute learned networks but don't learn themselves.
Largely, yes, for those specific examples. However, many others do incorporate on-chip learning. Spinnaker and Loihi, for example, can be programmed for various plasticity rules, including different forms of STDP, pairwise, triplet, allowing for adaptation based on spike timing. Brainscale S supports Hebbian learning in STDP through this analog synapse circuits. Dynapt SL is notable for its dedicated plastic core enabling on-chip, online learning using spike-driven rules like the Brader model, and also short-term plasticity effects. Parka implements learning rules like stochastic gradient descent directly by modulating the RM resistances. And the transistor channel systems demonstrate LTP, LTD, and STDP through the analog physics of their floating gate synapses. The dynap cell, Lewy, and the transistor channel systems perhaps represent the most advanced examples of integrating complex online learning directly into the hardware fabric.
That's a critical capability for true brain-like intelligence, isn't it? Because brains don't download software updates. They learn continuously from experience. Let's move on to how these systems handle internal communication, their routing strategies. How do they move those postcards, those address events or packets around their vast networks efficiently?
Getting communication right is absolutely crucial, especially at scale. Many systems, including the IFAT family, DynapsEL, and the transistor channel systems, rely heavily on the address event representation (AER) protocol we discussed, essentially broadcasting neuron addresses when they spike. To handle the sheer scale of potentially billions of neurons, hierarchical routing is a common and necessary strategy. Higher IFAT uses multi-tree structures. Deep South organizes communication based on its mini-columns and hypercolumns. DynapsEL uses its three-level routers, intra-core, intercore, interchip. Lowy employs a hierarchical mesh protocol. These hierarchical approaches are vital for reducing communication bottlenecks and efficiently routing events in large-scale networks, mimicking how the brain likely handles communication across different scales.
So hierarchy helps manage the traffic. What other approaches are used?
Other strategies include crossbar or mesh architectures, seen in Parka, the transistor channel systems, and True North. These allow for very dense, often local, connectivity, good for matrix-like operations. Brainscale, with its unique wafer scale integration, uses direct metal interconnects across the uncut wafer itself for extremely high-speed accelerated communication between its ICANN chips. And let's not forget the 2DI FWTA, where critical hardwired recurrent connections for local interactions are used specifically to avoid AER bus overload for those dense, fast, local competitive dynamics. They prioritize speed for specific connections.
It's clear that the way they send information around is just as important, maybe even more important at scale than how they compute it. Finally, let's talk about the abstraction level, how closely each system actually tries to mimic biological reality. Does it model the physics of ion channels or use more abstract neuron models?
This varies widely, and it really depends on the research goals and the specific problems they're trying to solve with the hardware. It's a spectrum. Some systems aim for very high biological fidelity. Brainscale S, for example, emulates the detailed ion channel dynamics described by the ADAX model. Spinnaker can also simulate complex, multi-compartment neuron models if needed. MFAD, as we heard, models the diverse spiking behaviors of Mihalis-Niebuhr neurons, offering 9 distinct firing patterns that are much richer than simple integrate and fire. Brainscales, DynapsCell, and Loihi use ADAX, or adaptive integrate and fire models, capturing more complex neural behaviors like adaptation and bursting. Deep South uses a simpler leaky integrate and fire (LIF) model, but scales it to billions of neurons by exploiting the cortex's modular structure. 2DI FWTA also uses LEAF, but focuses on the network-level WTA dynamics. The transistor channel systems and neurogrid, perhaps, aim to physically resemble biological neurons most closely in their fundamental operating principles by modeling MOSFET channels like ion channels, using the silicon itself as a physical analog of the cell membrane. And then at the other end, you have systems like True North, which uses a higher extraction, more deterministic model of a neuron, focusing on digital efficiency and scalability for specific tasks.
So it's clear there's a huge spectrum here, from systems that directly mirror the physics of biological neurons, like the transistor channel approach, to those that model neural computation at a higher, more abstract level, like True North. It truly seems like the best system really depends on what problem you're trying to solve and where you are willing to make those critical engineering trade-offs between fidelity, scale, power, and learning, doesn't it?
Absolutely. And this raises an important, maybe even philosophical question for the entire field. Are we ultimately aiming for a functional replica of the brain, perhaps to understand consciousness or disease? Or are we simply aiming for more efficient computing inspired by the brain's principles to solve practical AI problems better? The trade-offs between biological fidelity, scalability, power consumption, and on-chip learning capability are right at the heart of current research and debate. Each deep dive into these different processors, each unique architecture, contributes a valuable piece to this grand puzzle. They're all pushing the boundaries of what's possible in both artificial intelligence and computational neuroscience, whether it's understanding the brain itself or building the next generation of intelligent machines for the real world. Hashtag outro.
What an incredible deep dive into this quest to mimic the brain. We've seen how neuromorphic engineering isn't just some far-off futuristic concept anymore, but a rapidly advancing field delivering tangible breakthroughs today. From the mind-bending wafer-scale integration in brain-scale as running simulations at light speed, to the sophisticated on-chip learning of Dynap SCL, and the fundamental physical neuron modeling of the transistor channel systems. These approaches are fundamentally redefining the future of computation. It's really a testament to human ingenuity, deeply inspired by billions of years of biological evolution.
Indeed. The ongoing challenge is immense, make no mistake. Building something even remotely as capable as the brain is incredibly hard. But the progress is truly inspiring. As we push the limits of silicon technology to emulate the intricate dance of neurons and synapses, we're not only building potentially more powerful and vastly more energy-efficient computers, but we're also gaining deeper insights into the very nature of intelligence itself. The interplay between trying to understand the brain and engineering systems inspired by it is a profoundly synergistic relationship. It's a true scientific frontier, where engineering meets neuroscience, meets AI.
So, as you go about your day, maybe consider this. If the human brain is the ultimate low-power parallel supercomputer perfected by evolution, and these neuromorphic processors are genuinely on a path to replicate its incredible efficiency and learning capabilities, what fundamental questions about intelligence, maybe even consciousness, might we unlock when we finally build a system that truly operates like a brain? Will we simply have a powerful new tool, or will we have created something fundamentally new entirely, something that can learn and adapt in ways we can barely imagine today?
It's a profound question, isn't it? It resonates right at the intersection of science, engineering, and philosophy, inviting us all to ponder the very essence of what it means to think, to learn, to be intelligent.
We hope this deep dive has given you a useful shortcut to being well-informed about these fascinating large-scale neuromorphic spiking array processors. It's a field worth watching. Keep exploring, keep questioning, and join us next time for another deep dive into the knowledge that matters.